Hello everyone, respected chairperson and also fellow participants. It is a great pleasure to be here today. My name is Sonda. I am an undergraduate student from the Department of Biology, Universitas Pendidikan Indonesia. Today, I would like to present my narrative review. This review discusses how nanoparticle can improve breast cancer treatment, especially in overcoming multi-drug resistance. Without further ado, let's begin with the introduction. Breast cancer is one of the leading causes of cancer-related death among women worldwide, with around 2.3 million new cases and 685,000 deaths. One of the biggest challenges is multi-drug resistance, where cancer cells become resistant to chemotherapy. Conventional anti-cancer drugs have several limitations, including poor solubility, low bioavailability, and instability. Lipid nanoparticles can overcome these limitations by protecting the drug from degradation, increasing bioavailability, and improving drug accumulation inside cancer cells. This review has three objectives. First, to evaluate the potential of lipid nanoparticles for treating drug-resistant breast cancer. Second, to identify the most promising lipid nanoparticle formulation. Third, to identify research gaps that can guide future studies. This review was conducted using the PRISMA approach. Articles were selected based on inclusion criteria such as publication between 2021 and 2026, original research, English language, open access, and SGR indexed journals. Finally, 5 articles meet all eligibility criteria. In the next section, I will summarize the findings from the 5 selected studies. The first 3 studies are from Wang et al., Gu et al., and Bauer et al. They investigated different lipid nanoparticle formulations to overcome multi-drug resistance. The remaining studies are Najari et al. And Hashim and Rajab. The studies mainly focused on nanostructured lipid carriers for improving drug delivery and formulation performance. Overall, the studies show a clear trend toward developing lipid-based drug delivery systems with molecular targeting. Different formulations, including SLNs, NLCs, and hybrid nanoparticles, were designed to improve drug delivery while reducing multi-drug resistance. Several characterization techniques were used. Time-observed particle morphology (DLS) measured particle size and zeta potential, while UV spectroscopy measured drug concentration and encapsulation efficiency. FTIR confirmed chemical interactions, FISM observed surface morphology, and flow cytometry analyzed apoptosis and cell characteristics after treatment. Cell culture was maintained using an incubator. Electrophoresis separated DNA or proteins, while the ELISA reader was used to evaluate cytotoxicity and cell viability. The studies used different formulations and preparations methods. Overall, there is a technological shift from conventional SLNs toward NLCs and hybrid nanoparticles because they provide better stability and drug loading capacity. This figure summarizes the general workflow of lipid nanoparticle development, starting from formulation, characterization, biological evaluation, and finally validation of therapeutic efficacy. Time image showed that most nanoparticles had spherical morphology. TPGS SLNS appeared more homogeneous, while PONLC and ANZ NLC showed slightly larger particles with different internal structures. Particle size ranged from approximately 21 to 203 nanometers. The smallest particles were reported by Bauer et al. With an average size of about 21 nanometers, which is beneficial for better tissue penetration. Zeta potential indicates nanoparticle stability. Among the formulations, PONLC showed the highest stability with a zeta potential of approximately minus 21 millivolts, indicating a lower risk of particle aggregation. This dose-response curve demonstrates that increasing nanoparticle concentration reduces cancer cell viability. In other words, higher doses produce stronger cytotoxic effects. This graph compares different formulations after 48 hours of treatment. Lower cell viability indicates stronger anti-cancer activity, and nanoparticle-loaded formulations generally perform better than free drugs. This flow cytometry analysis evaluated apoptosis after treatment more cancer cells in third, early, and late apoptosis, indicating that the nanoparticles effectively induce programmed cell death. This graph summarizes the apoptosis percentages obtained from flow cytometry. The treated groups showed significantly higher apoptosis than the control, confirming improved therapeutic activity. Western blot analysis showed reduced expression of proteins associated with multi-drug resistance and metastasis. This suggests that the PGS/SLNS can help reverse drug resistance. This study analyzed apoptosis-related proteins. The combination treatment increased pro-apoptotic proteins while decreasing anti-apoptotic proteins, indicating enhanced cancer cell death. This study evaluated LDLR and SRB1 receptor expression across different breast cancer subtypes. Different receptor expression patterns suggest opportunities for more targeted nanoparticle delivery. Flow cytometry showed that PONLC caused cell cycle arrest in the C phase. This prevents DNA replication and inhibits cancer cell proliferation. Although the results are promising, several limitations remain. Most studies lack long-term toxicity evaluation, in vivo validation, or testing across multiple breast cancer subtypes. Each study has different strengths. Some provide comprehensive biological validation, while others focus on formulation optimization. However, most studies still require further biological and clinical validation. In conclusion, lipid nanoparticles are promising drug delivery systems for overcoming drug-resistant breast cancer. LDL-DHA showed the smallest particle size, PONLC demonstrated the highest stability, and TPGS-SLNS, together with EPLNs, showed strong potential for reversing multi-drug resistance. However, further in vivo studies and long-term safety evaluations are still needed before clinical application. These are the references used in this narrative review. That is all. Thank you very much for your attention.